The last section that we have in this is also about arguments, but a different type of argument. So in section 3.6, we finish with what's called syllogistic, which I don't think I can spell. Oh, I have it. Confidence. Syllogistic arguments. Syllogistic arguments are based on quantitative statements. And so just to refresh your memory, because this is where we started in the first section, okay, one of the first things we talked about were quantitative statements. They're statements that start with either the word all or some or none. And I'm just going to give you a little hint, studying for your test. Okay, I do have a couple problems where I ask you to negate those qualitative arguments. Remember that the negation of an all is not none. The negation of an all statement is some are not. Okay, so go back into your notes and refresh your memory on that, because there's 2 questions on the test on negating quantitative arguments. So quantitative statements. Syllogistic arguments are based on those quantitative statements. And the nice thing about these arguments is we're going to draw pictures. Okay, so the way that we do this is we use what's called Euler diagrams. It looks like Euler, but he was German, and so it's Euler. They're very similar to Venn diagrams. Okay, Euler diagrams, just all they do is they represent the relationship between two statements. So I'm just going to start with 3 examples of the different types of Euler diagrams, and then we're going to go through, we're going to do some of those examples on the sheet that I just gave you. And if you're watching the video, the sheet is in Canvas. Open it up, print it off, and you'll be all set. So the first one I'm gonna do is this. I'm gonna say, okay, all dogs are brown. It's a quantitative statement, starts with the word all. All dogs are brown. So what an Euler diagram is this? Again, just like a Venn diagram, you got a box around it that represents the universe of everything. So then here's going to be the question that we're going to answer, and this will be something that becomes part of our practice. For an all statement, whenever you have an all statement, okay, that means you're going to have 2 circles, one inside the other. Okay, so it's going to look like a fried egg here in just a second. So there we go. I got 2 circles, one inside the other. Here's what I need your help determining. This is the learning right here. One of these circles is going to represent dogs. One of these circles is going to represent brown things. Which one is going to be which? Is the smaller circle going to be the dog circle, or is the smaller circle going to be the brown circle if I say all dogs are brown? Which one did I say? Dogs. Okay, good. I'm glad, because you're right. Yes. Okay, so all dogs are brown means that the dogs are represented by the small circle, and then the brown things are going to be the bigger circle. Because the way this statement is written, okay, if you reverse the circles, if I put the brown right here, and then I put the dogs, well, you've got the dog circle is bigger. That means there's dogs out here that are outside of the brown. Okay, so there would be other colored dogs, red, yellow, black, white, whatever. Okay, so that's why that one. Does that make sense? Why it goes like that? You tracking with me? Okay, I'm seeing some nodding. Just to let you know, anytime you see an all statement, whatever one comes first is always the smaller circle. It's good to make note of that, because some of the examples you're going to do, there's going to be some goofy things, some goofy statements, because the book's wanting to know, do you understand what's going on, or are you just using some prior knowledge of these objects that we're talking about? Okay, so the second quantitative statement that we're going to draw an Euler circle for is some dogs are brown. All right, let me ask the question in a different way. If some dogs are brown. I'm going to have a dog circle. I'm going to have a brown circle. How do you think these two circles are going to interact with each other if the quantitative statement is some? Ooh, yeah, it's going to look like those Venn diagrams that I gave you a whole sheet worth, if you remember that. So some dogs are brown. We're going to have a dog circle right here, and then we're going to have a brown circle right here. So just help me out. This is slightly related to the set stuff that we talked about. So then how would I describe this part of the circle? How would I describe this part of the dog circle? Perfect. And then how would I describe this part of the circle? Perfect. Yeah, you guys are got it. Good. Either I'm doing a good job or you guys are just amazing. So it's probably a little bit. All right, the last one. No dogs are brown. Okay, so I just have enough room. I probably should have started a little more left than I did, but that's okay. So again, I'm going to have a dog circle. I'm going to have a brown circle. If no dogs are brown, how do you think these two circles are interacting? They're not touching. Yeah. So once you understand those are the only three things you're going to see, with one exception. Sometimes when you're doing these syllogistic arguments, okay, you're either going to have a quantitative statement as one of your premises, or then you're going to have something in particular. So for instance, if I have all dogs are brown, and then I say something like Sam is a dog. So this is a particular dog, okay? So this is not a set of things named Sam. This is just a particular dog. I'm just going to make a little X. Where am I going to put my X? If Sam is a dog, the X is going to go where? Yeah, so this would be Sam right here. So that's going to be the key to whether a syllogistic argument is going to be valid or not. So we're going to do some drawings, and what our goal is when we've done our drawing of the premises, does the conclusion have to be what is on the paper? Is that the only conclusion that you can come to? Okay, so let's come over here. I'm going to change cameras because I have that sort of power now. I'm really enjoying it.
And then I'm going to give you a better view. There we go. All right. So going to start with the first one. So just like our symbolic arguments that we were doing with logic, the same sort of thing holds. This is my example. All college courses are fun. MGF 1106 is a college course. Therefore, MGF 1106 is fun. Just to let you know, these first two things are called the premises, just like before. And then what comes after the therefore, this is the conclusion, just like before. So no difference in terminology from the previous section. That's good. I would hate to have to change the terms. So the way you do a syllogistic argument, and I'm just going to be really clear about this, you draw the premises. You draw the premises. That is the thing that you have to do. You don't draw the conclusion. What you want to do is you want to see, does the conclusion naturally follow when you draw the premises? Or are there other conclusions that you could come to? So for instance, for this one, I'm going to go, all college courses are fun. So here's my Euler box right here. I need a circle for college courses. I need a circle for fun things, just like we saw on the example a moment ago. So it's an all statement. So because it's an all statement, I have one circle inside the other circle. Which circle is going to represent the college courses and which circle is going to represent the fun things? Perfect. Yes. I'm just going to use the word college here because, and then I'm going to put the word fun right here. Now, this is an example where my second premise is a specific statement. It's not another circle. Okay, there's some of each on here. The second one is MGF 1106, the class that you presently are sitting in, is a college course. So I'm going to put an X somewhere in my Euler diagram. Where am I going to put an X? Okay. Now, before we look at the conclusion, here's my question to you. Is there anywhere else that it would have made sense to put the MGF 1106 X? Could I have put the MGF 1106 out here? No, because the MGF 1106 is a college course, right? It has to go in this circle. So the MGF 1106 couldn't go just outside here because then it wouldn't be in the college circle. The MGF 1106 can't go out here because it wouldn't be in any of the circles. So I'm just what I want you to become aware of, and as we do more examples, this will be clearer. I just want you to become aware of making sure that wherever you put your circle or you put your X is the only place it could go. So let's look at the conclusion. Now remember, I'm not drawing the conclusion. I put my pen down at this point. From the drawing, is this the conclusion? Do I have to come to the conclusion that MGF 1106 is fun? It's in the fun circle. In my drawing, is MGF 1106 inside the fun circle? Yeah, here it is. The fun circle is around the college circle, right? So it has to be there. So that is a valid argument because MGF 1106 has to be in the college circle has to be in the fun circle, so by extension, MGF 1106 has to be in the fun circle. Okay, you'll get used to this. I understand the first couple are always a little shaky when we do this. So what I would like you to do is do your best job, okay? You might get this next one wrong because it's only the second one you've done, but give your best shot at example 2. All right, let's give this a shot together, and then we'll do another one. So here's my Euler box. Nice and purple. So the first statement is some nurses work in pediatrics. So this is a sum statement. So I'm going to have 2 overlapping circles. And so it doesn't matter left or right. I'm going to put nurses on the left. I'm going to put pediatrics on the right. We good so far? Okay, Lisa works in pediatrics. Okay, now don't assume extra information. Lisa works in pediatrics. Does it say anything else about Lisa? Don't worry about the conclusion. Where could Lisa be in the pediatric circle? Can Lisa be right here where I made an X? Could Lisa be right here where I made an X? Right, either of those match with the statement Lisa works in pediatrics. Would you agree with that? Okay, this is what I was implying in the previous example. Making sure that where you're putting your X or your circle is the only place it could go. Okay, so this one, Lisa could go in either of those places and you have not violated either of the premises. Okay, so both of the premises are good. So now the conclusion is the only conclusion that I can come to is the only conclusion that Lisa is a nurse. Does that have to be the conclusion? Right, exactly. Lisa could be a nurse, right? If she's in the intersection right here, but Lisa could be a doctor. Lisa could be a patient, right? I mean, it could be, or I guess not because it says works. I don't know. Lisa could be anything else, okay, out here. So that's why this one is invalid. No, if it said some are not, you would draw the same sort of thing. Yeah. Does that make sense? We doing okay? Do you understand why that one is invalid? Like why? Because of the drawing. We doing okay? All right, we'll try the next one. Example 3. Example 3 is another one with a particular thing in one of the circles. And then we'll talk about what if the second premise is another circle. It's even more fun. Yes, example 3, please. This one says, first, all ballerinas are athletic. So it's an all statement. So I have one circle inside the other circle. And so which one's the smaller circle according to my statement? Okay, the ballerinas, I'm going to abbreviate that BALL just because it's too long of a word. I should have picked a shorter word. And then athletic right here. Okay, fantastic. Russell is athletic. So which, well, clearly, Russell's in the athletic circle. Am I told anything else about Russell at that point? So can Russell be in here and still be athletic? Could Russell be here and still be athletic? Yes. Again, I wanted to give a second instance now that we're seeing this. So in this case, is the conclusion I have to come to that Russell is a ballerina? Yeah, Russell could be, right? But Russell doesn't have to be. It's not the only conclusion that I can come to, and that's why it's an invalid argument right there. So I just wanted to give you a couple of examples because sometimes students stumble with how do I know if it's invalid? It's anything that there is more than one option for where something could go. All right, I'm going to do example 4 along with you. Example 4 has more than one circle, so that makes it more fun than the other ones. So I'm going to draw my Euler box right here. Okay, my pen's running out of ink. That's bad time. It's not really out, it just doesn't want to write anymore. Okay, we'll come back to you. Okay, the first statement says, all Earth people have 2 arms. Okay, so there we go. So all is one circle inside the other. And I think you would tell me that the Earth people, we'll just put Earth right there. And then 2 arms, we'll put that on the outside. Okay, now here we go. You got to help me on this next one. The next one says all people with 2 arms can fly. So I have a new circle. I've got a fly circle. Where's the flying circle going to go? In relation to, forget the Earth circle, nothing's been said about that. Where is the flying circle going to go with respect to the people with 2 arms? Yeah, why around it? All people with 2 arms, remember I told you the way an all statement works is whatever comes right after the all is the smaller circle. So the 2 arms, that's the smaller circle. So fly goes around it. Is that the only way that I can draw that? I just want to confirm. Okay, and the answer is yes, but we're looking at this. Okay, I'm just trying to get you to ask that question as you're going through and get more experience in this. Okay, so there's no other way I can draw that. Like the fly circle has to go around the two arms circle. It can't cut into it. It's not a sum statement. So is the only conclusion that I can come to that all Earth people can fly? Is that what the drawing tells me? Is the whole Earth people circle inside the fly circle? Yes. So this is a valid argument. There's no other way that drawing could be done. I'm sorry, what? No, this is a little bit different. Great question. This is different because I've got both my premises are quantitative statements. So when they're quantitative statements, you use circles. And that's different than the other examples where the second premise has been a specific thing, like Russell is athletic, Lisa works in pediatrics, MGF 1106 is a college course. So those weren't circles, those were something in particular in a circle. Does that make sense? Yeah, that's a great question. I'm glad you asked that. All right, let's try example 5. It's very, very similar, but I just want you to have the fun of drawing. Premise number 1 is all dolphins are mammals. So I've got my dolphins circle, I've got my mammal circle. So I'm just going to use the letter D for dolphin and M for mammals. All mammals are vertebrates. So again, I need a new circle. There's another, the second premise is a quantitative statement. So my new circle, vertebrates, where is it going to go with respect to the mammal circle, inside or outside? It's going to go outside because, again, the mammals comes right after the all, so it's the smaller circle. So there's my vertebrates. So do I have to come to this conclusion? Are all dolphins vertebrates? Are all the dolphins inside the vertebrate circle? Yes. Okay, so that basically that was the same argument we just did in example 4 with the Earth people flying around. But I just wanted, again, to make sure that you're drawing everything. Please do example 6. Give it your best shot. See how you can do. All right, so the first one says some caterpillars have fur. So that quantitative means that I'm going to have 2 circles that overlap. So here's my caterpillar circle. Here's my things that have fur circle. Okay. The next one says it's an all statement. So all things with fur are mammals. So I need a new circle. I need a mammal circle. Where's the mammal circle going to go? Yep, it's going to go around the fur circle. So something like this. Whee! So is the conclusion that I have to come to that some caterpillars are mammals? Yes, they have to overlap somehow. So that is going to be a valid argument. Even if you drew the mammal circle bigger, you'd have some of the caterpillars, at least some of the caterpillars would be mammals. So there you go. All right, we've got two more. We've got plenty of time. So we're going to go ahead and finish up these last two. So go ahead and do example 7 about marigolds and tulips and all sorts of fun flowers. You can go ahead and do 8 if you want. That's fine. They don't, once you get the hang of it, they don't take too long to do these. All right, so 7 says all marigolds are annuals. So I have an all statement. So I need one circle inside the other circle. So marigolds and annuals. Okay, great. Some tulips are annuals. So now I need another circle for tulips. And how is that tulip circle going to relate to the annual circle? I didn't hear all of what you said because of the mask, but I think you said that it's going to intersect with the annual circle, but then you said something about the marigold circle. Okay, so here's the thing. To me, this is the hardest problem of the syllogistic arguments. Okay, because does this premise right here, this second one, does that say anything at all about marigolds? It says it just says that the tulips and the annuals have to overlap. So I'm going to draw, actually, let me do 2 different colors here because the tulip circle could actually be 2 ways. We don't know. It's kind of like when you have that particular thing of Lisa being in pediatrics. Lisa could have been in one place or another. Yeah, you're right. The tulip circle could do this, right, where it just intersects a little bit, or we're not told, or the tulip circle could do this, where it also intersects with the other one. We are not told. Okay, so we can't assume extra detail. So because of that so in both of the circles that I've drawn, both of those tulip circles do not violate the idea that some tulips are annuals, right? They both accurately reflect this premise right here. This circle represents some tulips are annuals. This circle right here represents some tulips are annuals. But they have different conclusions, and that's the problem. Okay, so do I have to come to the conclusion that some tulips are marigolds? No, not in this case right here. Can I come to that conclusion? Yes, if this is the circle right here. That's why this is an invalid argument, because there's more than one possibility.
So if we drew both of those circles on the test, would you kind of?
No, that's the exact right answer. No, that's what you would want to do, because you'd want to show me, hey, Perkster, the reason this is invalid is because that tulip circle could go either way without violating the premise. Okay, so that's what makes this invalid, is both of those tulip circles are correct.
And then if you only drew one circle, that'd be wrong.
I wouldn't, depends on what you told me afterward. I mean, if you drew the one circle and then said, but hey, the tulip circle could be, it could intersect, so this is invalid, I would give you credit for that. But if you wrote valid, a valid argument, I would then thumbs down on that one. All right, last one. All Call of Duty players are students. So here's the Call of Duty, here's students. Joel is a Call of Duty player. We've seen this argument. Joel has to be inside that middle circle. And so therefore Joel is a student, and then that's going to be a valid argument. Yes, Joel has to be in the student circle because he has to be in the Call of Duty circle. All right,